Hello, my name is Nas, and today we're going to talk about planetary motion. First of all, let's go through Kepler's laws. We should know that, in fact, orbit of motion is an ellipse, not a circle, and this ellipse has x and y axes, and two foci points. One of them is Sun. So we also have a term called eccentricity. Eccentricity shows the distance between Sun and foci, and when the distance between Sun and foci is minimum, like 0, the eccentricity will be 0, and this ellipse will become a circle. But while this foci and Sun have a huge distance, the maximum eccentricity will be 1. We also have a term called perihelion and aphelion. So aphelion is a point of Earth's orbit that is farthest away from the Sun, and perihelion is a point of Earth's orbit that is nearest to the Sun. Overall, Kepler's first law sounds like this. The orbit of planet is an ellipse with the Sun at one of the two foci. While the second law states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. So how it is possible? Explanation is very easy actually. When the planet is closer to the Sun, it moves faster. However, when it's far away, its velocity decreases. In this picture, the number of points is equal to the period. It can be observed that points are concentrated near the foci. To understand the third law of Kepler, we should imagine that these 3 points are Sun and 2 planets. The distance between first planet and Sun is R1. The distance between second planet and Sun is R2. And the period of rotation for planet 1 is T1 and for planet 2 is T2. So this law states that when we cube the first radius and divide by square of period of the first planet, it will be equal to the cubic radius of second planet divided by square of period of second planet. So let's explain how Kepler got this formula. Let's write the value of gravitational force, centripetal force. Because of equality of these forces, we can get the value of velocity. This gives you a value of velocity of planet moving around the Sun in terms of its orbital velocity. And here m, it is a mass of Sun, e is gravitational constant, and r is radius. But we also know the formula of velocity, which equals to 2 pi radius divided by t, which is period. So then we can square these two formulas. As a result, we will get that cube of radius divided by square of period is equal to gravitational constant multiplied by mass and divided by 4p squared. On the right side of the formula, all of them are constant, including gravitational constant, mass, and pi. Finally, let's derive Kepler's equation. So we should understand that ellipse is squash circle and it has its semi-major and semi-minor axes A and B. On a graph, E means eccentric anomaly. In orbital mechanics, eccentric anomaly is an angular parameter that defines the position of a body that is moving along an elliptic Kepler orbit. And mean anomaly is the angle between barycenter and position of planet. To derive Kepler's equation, we should write down area formula for S and S1, shown on the pictures. S1, which is larger than S, is equal to the area of a sector minus area of triangle. Area of sector will be half a squared multiplied by eccentric anomaly minus half of a multiplied by eccentricity and sine eccentric anomaly. And S is proportional to S1, so we can multiply S1 by B divided by A. Using proportion, we can find formula of mean anomaly, which equals to 2 pi S divided by S ellipse, and S ellipse is actually equal to pi AB, which are my major and minor semi-axes. This will lead us to derivation of Kepler's equation. Actually, now we can solve this equation using Newton's iteration method, and also Using formulas for x and y, we can receive the coordinates of planet at any given date and make predictions about its coordinates. Let me show you an Unity application where you can enter any date, like for example, June 2003. So planets will change their positions and correspond to the coordinates on this date. Kepler's law and equation have played an important role in history of both physics and mathematics, particularly classical celestial mechanics. Thank you for watching. I hope that you enjoyed this video.